we're going to look at a few different indeterminate forms of limits. So the first one here is the limit as x approaches infinity of x sine 5 over x, which is of the form infinity times the sine of 5 over infinity, or the sine of 0, which is just 0. So when we have a form of infinity times 0, what we want to do is we want to rewrite it so that it becomes either 0 over 0 or infinity over infinity. And then we can apply l-Hopital's rule. So we'll rewrite this as the limit as x approaches infinity of the sine of 5 over x divided by 1 over x, which is equivalent to the original limit, but is now of the form 0 in the numerator and 0 in the denominator. So we have the indeterminate form 0 over 0, which means we can apply l-Hopital's rule and get the limit as x approaches infinity of the derivative of sine of 5x, which is cosine of 5 over x, times the derivative of 5 over x, which is negative 5 over x squared, divided by, in the denominator, the derivative of 1 over x is negative 1 over x squared. So we can quickly cancel out both the negative signs and the x squareds in the denominator. The 1 in the denominator no longer matters, and we're just left with the limit as x approaches infinity of 5 cosine 5 over x. And when we plug in infinity, we get 5 times the cosine of 0, and the cosine of 0 is 1, so our final answer is just 5. Our next indeterminate form is 1 to the infinity. So if we plug in 0 here, the base of our exponent becomes 1, and our exponent is 2 over 0, which is infinity. So a form that is 1 to the infinity, we need to, instead of evaluating this limit, we need to look at the limit of the natural log of this function, because we know that the e to the natural log of u is just equal to u. So if we look at the natural log of the function, we can get rid of the exponent, pull it out to the front, and we'll end up with a limit of a similar function of the natural log of our function. And at the end, all we have to do is just raise our answer as a power of e. We'll exponentiate our answer. So let's take the natural log. So it's the natural log of 1 plus 3x to the 2 over x. So we're just looking at this. This is not going to be our final answer. And when we do this, we can pull our exponent of 2 over x out to the front, and we have 2 over x ln 1 plus 3x. And if we look at this, this is now 2 over 0 times the natural log of 1, so that's infinity times 0. But we can really quickly change that just like we did in the previous problem. We can drop the x into the denominator and get the limit as x approaches 0 of the natural log, or 2 times the natural log, of 1 plus 3x all over x. And now we're in the form 0 over 0. And we can use l-Hopital's rule to rewrite this as the limit as x approaches 0 of the derivative of the top, which is 2 over 1 plus 3x times the derivative of 1 plus 3x, which is 3, all divided by the derivative of x, which is just 1. And we end up with 6 over 1 plus 3 times 0. The 1 in the denominator can be ignored. And we have 6 over 1, or 6. But we have to remember that this is not our final answer, because this is the limit of the natural log of our function. So the limit as x approaches 0 of our original function, 1 plus 3x, to the 2 over x is equal to e to this power, e to the 6th power. And this is the method we want to use for any 1 to the infinity indeterminate limits. For this next one, when we plug in infinity, we've got the form infinity to the 0 power. And so for this one, we'll look at the same method as the previous problem. We'll take the natural log of our function and look at that limit, and we'll have to exponentiate our answer at the end. So we will look at the limit as x approaches infinity of the natural log of 3x to the power of 2 over x. And as we go through and do this one, first thing that we'll need to do is we'll need to separate this natural log of 3 out of it, because the 3x is not being fully raised to the power of 2 over x. So this will become the limit as x approaches infinity of the natural log of 3 plus the natural log of x to the 2 over x. So for the first part of it, the limit as x approaches infinity of natural log of 3, well, that's just natural log of 3. And for the second part of it, we'll bring the 2 over x out to the front, and we'll have a limit as x approaches infinity of 2 over x, natural log x. And this one is 0 times infinity, and so we'll rewrite it as the limit as x approaches infinity of 2 ln x over x. And as we continue doing this, we end up with infinity over infinity again, and so we will use L'Hopital's rule. So we've now got the natural log of 3 plus the limit as x approaches infinity of 2 over x, that being the derivative of 2 ln x, all over 1, which gives us the natural log of 3 plus, and then when we plug in our infinity here, we end up with 2 over infinity, which is 0. So we've got the natural log of 3 plus 0, and if we exponentiate that, that's just e to the natural log of 3, which is just 3.